For the longest time, we thought about artificial intelligence like, well, brain in a jar.
Right.
You type a question into a little text box, it thinks for a second, and it types a pristine, helpful answer back to you on a screen. It was contained, It was purely informational, just a chatbot.
Yeah, it was a passive oracle. I mean, you had to initiate every single interaction, and its entire universe existed totally within the confines of your browser window.
Exactly. But when you look at what is happening right now across the tech landscape, that jar is shattering. The brain is getting hands, it's getting eyes, and it is physically walking out onto the factory floor.
It really is.
So, welcome to the deep dive. It is crazy to think that in just one single week, this mid-March, a stack of updates completely rewrote the playbook for where this technology is heading. Today, we are looking exclusively at a pivotal week of NVIDIA AI updates, strictly from March 8th to March 14th, 2026.
It's a fascinating and honestly an incredibly dense window of time. What we're seeing in these primary sources, these technical blogs, security bulletins, enterprise reports, isn't just incremental software updates. Right. We are watching the underlying architecture of global computing fundamentally change to support this new era.
And the mission today is to show you, the listener, exactly why this specific week matters so much. Because we are witnessing the definitive shift from those passive chatbots to what the industry calls agentic AI and physical AI. And as we'll see, it's all being backed by mind-boggling gigawatt-scale infrastructure. So, okay, let's unpack this.
Yeah, to understand the shift, we really have to start at the absolute foundation, which is the models themselves. If you want an AI to be agentic, meaning it can execute multi-step workflows entirely on its own, making decisions, recognizing mistakes, and correcting course without human intervention, it needs to be able to think longer and harder.
It can't just lose the plot halfway through a task.
Exactly. It cannot lose the plot halfway through a complex problem.
Which is an enormous computational challenge. But NVIDIA released something globally on March 11th on their technical blog that seems designed to solve exactly that. The headline here is the launch of Nemotron 3 Super.
Yes, Nemotron 3 Super.
This is a massive open model designed specifically for complex agentic systems. And the sheer specs on this are wild. It features a 1 million token context window.
Let's actually put that context window into perspective, because it is the crucial part for agentic workflows. When an AI agent is working through a complex, multi-step problem, say, analyzing a massive financial data set, writing code to process it, and then debugging its own code, it generates a massive trail of its own internal reasoning.
Like it's talking to itself.
Exactly. NVIDIA's research notes that agentic systems can incur up to 15 times more tokens than standard chat just from talking to themselves to solve a problem.
Oh, wow. So holding a 1 million token context window, I mean, that's like holding an entire library in your head at once, remembering every single page you just read without losing your train of thought while you try to write a comprehensive research paper.
That's a great way to put it.
But I do have to push back here for a second. The other spec on Nemotron 3 Super is that it is a 120 billion parameter model. Isn't that incredibly heavy to run?
It sounds like it would be, yeah.
Right, because I thought the whole point of agents was that they needed to act fast and be economically viable. Running a 120 billion parameter model for every little autonomous task sounds like a financial nightmare.
Well, that is exactly the bottleneck the industry has been facing, and it is where the specific architecture of Nemotron 3 Super comes in. It uses what's called a mixture of experts, or MoE, architecture.
Okay.
To understand how it works, think of the model like a massive global corporation. If you have a highly specific legal question, you don't call an all-hands meeting and ask every single employee in the building to weigh in.
No,
right?
You just route that question directly to the legal department.
Precisely. Under the hood, the MoE architecture uses a sophisticated routing network. Every time a piece of data passes through, the router decides which specific expert neural networks are best equipped to handle it. So, out of that massive 120 billion parameter architecture, only 12 billion parameters are actually active during inference at any given moment.
Oh, I see.
You get the vast comprehensive knowledge of the entire corporation, but you are only paying the computational salary of the specific 12 billion parameter department working on the task.
That is wild. That drastically reduces what NVIDIA calls the computational thinking tax. And the metrics they publish are serious. They claim up to 5 times higher throughput and 2 times higher accuracy for complex agentic systems compared to their prior version.
Which is the exact threshold needed to make multi-step autonomous workflows actually viable at scale. But, here's the catch.
What's the catch?
Having a brilliant agentic model reasoning in the cloud is one thing. If you want these agents to step out into the real physical world, to control a robotic arm or drive an autonomous vehicle, they need to deeply understand physics. They need spatial awareness.
And how do you teach in AI physics? You build a world for it. Which brings us to a major global release from NVIDIA Research published between March 10th and 13th.
Right, the Cosmos updates.
Yeah, updates to the Cosmos World Foundation models, specifically Transfer 2.5, Predict 2.5, and Reason 2, alongside the publication of the Diffusion Forge paper for 3D scene synthesis.
These Cosmos models are essentially world models for physical AI. If you want a robot to navigate a busy warehouse, it needs to intuitively understand what happens if it drops a heavy box, or how friction works on a slick concrete floor.
Or how a human might unpredictably step into its path, right?
Exactly. But training a robot on that kind of physical interaction in the real world is almost impossible. You can't just have a $1 million robot bump into real walls a million times to learn spatial awareness. You have to train it in a simulation.
Yeah, that makes sense.
The problem is generating those 3D environments computationally has historically been incredibly slow and expensive.
Which brings us to the mechanism behind Diffusion Forge. From what I read in the technical blog, generating high-fidelity 3D scenes requires calculating how light bounces, how shadows fall, and how textures interact in real time.
Right, and traditional diffusion models, which generate 2D images, struggle massively to keep 3D frames consistent without flickering or hallucinating geometry.
So Diffusion Forge alters the mathematical approach to scene synthesis, streamlining how the AI predicts the geometry of a room. And the numbers published are striking. By optimizing that geometry prediction, Diffusion Forge reduces the computational cost of generating 3D environments by 40%.
That's a massive reduction.
It is. And more importantly, it hits 120 frames per second real-time rendering on the new Blackwell GPUs.
What's fascinating here is the meta-level loop we are entering. We are now using highly advanced generative AI to build photorealistic, physically accurate virtual worlds running at 120 frames per second, simply so that other physical AI agents can go to school inside them.
That is so wild to think about.
The robot agent learns real-world physics entirely inside a synthetic simulation.
It really is like the Matrix, but built entirely for warehouse robots and autonomous drones.
It is, but this introduces a massive logistical hurdle. So we have these incredible, highly trained models reasoning in the cloud, and we've put them through a rigorous virtual schooling system. Now, we place that digital brain into a physical 500-pound robotic chassis on a factory floor. What happens when the Wi-Fi cuts out?
Oh, man. Or what happens if that robot is about to accidentally drop a heavy car door on an assembly line? It simply cannot afford a 200-millisecond round-trip delay to send a request to a cloud server in another state, wait for the model to think, and wait for a command to come back.
Exactly. The latency alone makes it incredibly dangerous. It needs to think locally.
That is the core challenge of physical AI, and NVIDIA addressed it globally on March 10th and 12th with major updates to its Jetson platform and TensorRT Edge LLM, detailed on their developer blog.
Yeah, the Jetson platform is NVIDIA's hardware for embedded edge devices. These are the actual physical computers sitting inside the robots or the drones.
So we are moving the intelligence out of the cloud and pushing it directly to the edge.
Yeah.
I like to think of Edge AI like having a master chef right in your own kitchen.
Okay, I like that analogy.
For a long time, if you wanted complex AI reasoning, you had to order it from a massive cloud kitchen hundreds of miles away. You send the request, wait for the delivery driver, and just hope it's still hot when it arrives. Now, with these updates, the master chef is literally standing at your stove.
It is a great way to visualize it. This Jetson update allows entry-level hardware like the Jetson Orin Nano 8GB, which is a relatively small, accessible piece of silicon to run open generative models ranging from 2 billion up to 30 billion parameters entirely locally.
Wait. How do you fit a 30 billion parameter model on an 8 GB chip? That math doesn't seem to add up at all.
It sounds impossible, but it comes down to quantization and the Tensor Edge LLM update. NVIDIA has essentially figured out how to mathematically shrink the precision of the model's weights, compressing the file size significantly without stripping away the core intelligence.
Oh, wow.
Yeah, the update added full support for those mixture of expert models we discussed earlier, as well as the Cosmos Reason 2 models and advanced speech recognition.
So the robot can process complex spatial reasoning, understand spoken commands from a factory worker, and make autonomous decisions entirely on device. It completely severs the umbilical cord to the cloud, slashing latency to almost zero, and it keeps working even in a dead zone.
And it is vital to note that this push to the edge isn't just for heavy industrial robotics. Digital environments are experiencing the exact same localized shift. On March 10th, at the Game Developers Conference, NVIDIA introduced the Nemotron 3 Nano 4B.
That's a 4 billion parameter small language model built for local execution.
Wow.
They announced this alongside updates to their Avatar Cloud Engine, or ACE, and a feature called RTX Mega Geometry for dense foliage rendering.
If we look closely at the mechanism here, game developers can now embed highly interactive AI characters, NPCs, that can actually reason, remember past interactions, and hold dynamic, unscripted conversations directly into the game files.
So the processing doesn't happen on a remote server.
No, it happens right on the player's RTX graphics card sitting in their living room.
Even while the GPU is simultaneously rendering massive, dense forests using that mega geometry feature, it is the exact same principle as the Jetson robot on the factory floor, just applied to a virtual character in a digital world. Localized, instantaneous intelligence.
But whether we are talking about a local gaming PC rendering AI characters, a Jetson chip running a robot arm, or a massive cloud data center running a 120 billion parameter agent.
It all relies on one fundamental resource, which is silicon.
Right, and managing that silicon efficiently without wasting a single compute cycle is arguably the biggest bottleneck in the global economy right now.
Which brings us to a really illuminating piece published on March 10th. CEO Jensen Huang released an essay framing the modern era of computing as a 5-layer cake. The layers are energy, chips, infrastructure, models, and applications. He's making the case that AI is no longer just prepackaged software. It has transitioned into essential utility infrastructure.
And concurrently on that same day, they launched a product that perfectly illustrates the third layer of that cake, the infrastructure layer. NVIDIA announced the global availability of the RTX PRO server, powered by their Blackwell Server Edition GPUs.
And what makes this critical is technology called vGPU, or virtual GPU software. So what does this all mean for how work actually gets done?
Well, historically, if you were an animation studio or a massive engineering firm, you bought expensive, powerful desktop workstations for your staff. But when your artists or engineers clocked out and went home at 6 p.m., all of that incredibly expensive GPU compute just sat under a desk, idle and wasted.
Just burning cash, basically.
Exactly. The RTX PRO server centralizes all of that GPU power into the data center. By day, the vGPU software slices up the physical silicon virtually. An artist gets a virtual slice to do interactive 3D development or run those diffusion force simulations at their desk.
Right.
But by night, when the artists log off, the hypervisor instantly reallocates those exact same physical GPUs to run heavy, massive AI training models or batch inference workloads.
What does this all mean? They are essentially selling the entire bakery, not just the flour. They provide the chips, the networking, the virtualization software that slices it up, and the models that run on top of it. They are orchestrating the infrastructure so that utilization sits at 100%.
But centralizing all this compute into massive shared servers creates an incredibly high-stakes environment.
Oh, absolutely.
When the GPU becomes the core engine of the data center, handling the world's most valuable proprietary AI models, it also becomes the ultimate target for threat actors.
And the reality of that threat model hit hard during this specific week. On March 10th, NVIDIA issued Security Bulletin ID 5047 globally. They mandated emergency patches, specifically CVE 2025-33217 through 332-337, for severe vulnerabilities found deep within the GPU display driver and the vGPU software stacks we were just talking about.
These were not minor bugs where an app might crash. These were structural flaws in how the driver handles memory allocation.
Yeah.
Left unpatched, attackers could exploit these memory flaws to execute denial-of-service attacks, or far worse, achieve catastrophic, unauthorized escalation of host privileges in multi-tenant cloud environments.
Okay, let's pause there, because escalation of host privileges in a multi-tenant cloud sounds like intense cybersecurity jargon, but the implications are massive. Let's walk through how this actually works.
Sure.
If I am a malicious hacker and I rent a cheap virtual slice of a GPU in a public cloud, and a major global bank is renting another virtual slice of that exact same physical GPU board to process their proprietary financial AI model, wait, what does this vulnerability actually allow me to do?
It requires understanding how virtualized cloud architecture is built. Imagine the physical memory of the GPU as a series of hotel rooms.
Okay, hotel rooms.
The hypervisor, in this case the vGPU software, is the secure wall keeping the tenants completely separated. You only have the key to your specific room. However, if you can exploit a flaw in how the underlying driver allocates that memory, you can effectively break through the drywall.
You escalate your privileges from a restricted guest to the hotel manager.
Precisely. You escalate to the host level. Suddenly, you aren't just confined to your virtual slice, you have visibility and control over the raw physical silicon, which means, theoretically, you could monitor the computational cycles, access the data, or extract the weights of the proprietary models belonging to that major bank sharing the hardware.
Wow. So the graphics driver itself, the software we used to think just told a monitor how to draw pixels on a screen, is the weak link.
This raises an important question, right? Securing the AI hypervisor is now arguably just as critical as securing the core operating system itself. The GPU driver is the new arbiter of trust for global enterprise data.
It really is.
As AI workloads centralize, the security perimeter has fundamentally shifted down to the silicon management layer.
That is terrifying, but it really highlights the stakes. So we've covered the massive agentic models reasoning in the cloud, the push to local edge inference on Jetson to eliminate latency, the infrastructure required to virtualize the silicon, and the intense security required to lock it all down. Now, let's look at the business reality. Who is actually buying this ecosystem at scale? And is it actually driving real return on investment?
Well, the primary sources published this week answer both questions with a resounding yes. And the scale of the capital deployment we were talking about has officially shifted from megawatts to gigawatts.
Gigawatts, as in Back to the Future, 1.21 gigawatts of power.
Significantly more than that, actually. On March 11th, the NVIDIA newsroom announced a $2 billion direct investment into Nebius Group. The stated goal of this partnership is to deploy over 5 gigawatts of NVIDIA systems by the end of 2030 to build a full-stack AI cloud infrastructure.
5 gigawatts. And the day before that, on March 10th, they announced a multi-year deal globally with Thinking Machines Lab for at least 1 gigawatt of next-generation Vera Rubin systems, specifically dedicated to frontier model training.
Consider the profound shift in capital allocation this represents. These aren't just companies buying servers. These are nation-state level power commitments tied directly to hyperscale buildouts.
It's massive.
NVIDIA is pairing its next-generation architecture with direct capital investment to accelerate the timeline and aggressively lock in the global AI ecosystem.
But it's not just the cloud providers placing these massive billion-dollar bets. Traditional, heavy industries are deploying this tech because the ROI is suddenly undeniable. On March 9th, NVIDIA published a blog detailing how ABB Robotics, one of the largest industrial robot manufacturers on Earth, integrated NVIDIA Omniverse libraries into their Robot Studio suite.
This ties perfectly back to our earlier discussion about Diffusion Forge and teaching robots inside virtual worlds. By integrating Omniverse, ABB reported achieving a 99% sim-to-real correlation.
Okay, I have to stop you there. 99% sim-to-real correlation. That sounds heavily like marketing fluff. How can a virtual simulation perfectly account for real-world friction, sensor degradation, or the microscopic wear and tear on a physical robotic gear? The real world is messy.
I mean, it is a valid skepticism, but it speaks to the breakthrough in physical AI modeling. The Omniverse integration, powered by models like Cosmos Reason 2, isn't just drawing a video game environment. It is calculating exact material properties, the tensile strength of the metal, the precise slip of a specific rubber compound on a floor, the noise in a camera sensor caused by specific lighting conditions.
Oh, wow.
Because the simulation has that level of mathematical physical fidelity, ABB can program, train, and test complex robotic workflows entirely in software before ever touching physical metal.
And the business result of that digital twin testing. The blog states it cuts physical deployment costs by up to 40% and accelerates time to market by 50%. The immense friction and cost of physical trial and error on a factory floor is almost entirely removed.
And this brings us to the ultimate macro validation of the week. You take that 40% cost reduction from a heavy industrial player like ABB, and you look at the broader data NVIDIA released on that exact same day, March 9th, the Global State of AI Report 2026.
This was a massive survey of over 3,200 enterprise respondents, and the numbers here are striking. 64% of organizations globally are actively using AI in their daily operations. We are officially out of what they call pilot purgatory.
But the critical metrics are the financial outcomes. 88% of those organizations reported revenue increases attributed to AI, and 87% reported actual cost reductions.
Here's where it gets really interesting. When you realize that physical engineering companies like ABB are cutting deployment costs by 40% just by letting robots practice in a virtual matrix, suddenly that 87% enterprise cost reduction statistic isn't just a survey number.
Exactly.
It's the direct result of physical AI actually working in the real world.
Those figures definitively prove that enterprise AI is moving from experimental novelties to scaled operational deployment. The return on investment is no longer theoretical.
Yeah.
When you see 87% of companies reporting concrete cost reductions, those gigawatt-scale billion-dollar investments from Nebius and thinking machines suddenly make total economic sense. The massive demand for the infrastructure layer is entirely backed by the efficiency gains at the application layer.
So let's step back and look at what this single week of updates from March 8th to the 14th actually represents. We started with the foundation, Nemotron 3 Super, an open model utilizing a highly efficient mixture of experts architecture, uniquely capable of holding 1 million tokens in its head to execute complex, multi-step agentic workflows without losing its train of thought.
We then saw how those incredible reasoning capabilities are being pushed out of the cloud and directly to the physical edge.
Right.
Through the Jetson platform and Tensor Edge LLM, physical devices can now run localized, latency-free models, putting the master chef right in the kitchen where the work happens.
We saw how those physical robots are learning to navigate the world by training in hyper-realistic 120 frame per second digital twins using Cosmos and Diffusion Forge, allowing partners like ABB Robotics to cut their physical deployment costs by 40%.
And underpinning every single piece of this is an infrastructure strategy that has evolved into Jensen Huang's 5-layer cake. From virtualizing workflows so not a single compute cycle is wasted on RTX PRO servers, to aggressively patching the hypervisor security layer against sophisticated memory exploits.
All the way up to locking down gigawatt-scale cloud buildouts. For you listening to this, I want to emphasize that none of this is just distant tech news or abstract computer science. This is the foundation of the tools you are likely already interacting with at work. It is the invisible infrastructure that will power everything from your company's internal software suites to the autonomous logistics networks delivering your packages.
The transition from generative AI that simply writes emails to agentic and physical AI that executes tasks in the real world is happening right now. And the scale of the compute required to facilitate that transition is historically unprecedented.
Which leaves us with one final, unavoidable reality to chew on. We talked about Nebius deploying a 5-gigawatt AI data center. Just to put that number in perspective, 5 gigawatts consumes roughly as much power as an entire small country.
It's staggering.
As these AI agents get hands and eyes, as they leave the chat box and move into physical automation across the globe, the ultimate bottleneck for human progress isn't going to be the silicon. It isn't going to be writing better code or optimizing parameters. It is going to be the global power grid.
It is the first layer of the 5-layer cake for a reason. Without the raw energy to power the data centers, the rest of the technological stack simply cannot function.
Are we ready for the energy era of AI? Because that brain in a jar, it's out, it has hands, it's walking the factory floor, and it is going to need a massive extension cord. Thanks for joining us for the deep dive. We'll catch you next time.